So optimization then. So optimization algorithms generally are numerical techniques for locating the minima or maxima of some kind of objective function. So we seek the parameter estimate x tilde that is the argmax of some objective function, i.e. the combination that maximizes or equivalently minimizes this objective function x. And in our case, x is the vector of unknown parameters of some model that we're interested in. So we'll start thinking first of all about linear models and linear least squares. First of all, what do we mean by a linear model? So a linear model has the following, has the form written here. It expresses the signal for some combination of parameters and device x and device settings y as a linear combination of the unknown parameters x. The coefficients of those parameters in this linear combination are some function of these device settings y. So there's some different combination of those, not necessarily linear. The g's here are not necessarily linear, but some combination of the device settings y weighting linear contributions of each of the unknown parameters. And this linear system then turns into a nice simple matrix equation, which we can solve to get an estimate of the least squares of the best fit parameters in a nice simple way. Let me just work through that to spell it out a bit. So let's suppose we've got a number of different measurements then. Oops, wrong color. Let's suppose we've got a set of measurements A1 down to a big K. And so just the A1 is shorthand here. What I really mean by this is the measurement made for device settings K. Sorry, 1. So A1 is the set of measurements we make with a particular combination of device settings Y1, and similarly AK would be the measurement we make with device settings YK. So I'm saying then that we can write that, since we've got a linear model, we can write that as a linear combination of our unknown parameters. So I'm going to write that G11 x1 plus G12 x2 up to G1n xn, where G11 here then is again shorthand for this function little g of G1 of Y1. So G is a function of the device settings Y. For this particular measurement, the device settings are Y1, and G11 then is our function G1 of that first set of device settings. And I can write the same, a similar expression for each of these different measurements that I make, but the G's will be different because there are different device settings in general for each of my measurements. So it should be a GK, GK1, GK2, X2, GKN, XN. So hopefully you can see from writing out these linear, the linear model for each of these different measurements, how this simple matrix equation arises. So A then is this list of measurements up here. We can write our list of unknown parameters x1, x2, down to xn in a vector. And that leaves simply the matrix G, which contains all of these different big G coefficients that I've written up above, up here. So the matrix G would look like G11, G12, G1n, G22, oops, G21, 22, 2n. Okay, so that's where that linear system of equations comes from. So nice simple matrix equation then, A equals Gx. So how do we then, so all we've got to do now then is solve this for x to get our the list of parameter estimates that we're interested in. So can I simply pre-multiply both sides of this equation by the inverse of G to get that solution? Does that work? Answers in the chat, please. Not a square matrix, yeah, thank you, which means, of course, that it's not invertible. So I can't just simply take the inverse of it. I have to work a little bit harder to find a solution. Solution is actually here on the slide here. The standard trick is to instead pre-multiply both sides of this simple equation, first of all, by the matrix G transpose. I get G transpose A is G transpose G of X. This thing here is a square matrix. And so long as we've got, so long as the matrix G is of sufficient rank as many separate parameters as there are, or n, then it will also be invertible. So I can invert that matrix to get the solution X. This thing here is known as the pseudo inverse of G. It's such a common thing to want to do that actually there's a MATLAB function that computes it for us. And similarly, actually in most mathematical programming environments, there's a thing called P-in for pseudo inverse of G. So if we were writing this in MATLAB, we could simply write X is P-in of G times the matrix A, like so. And in fact, that's such a common thing to do as well that there's an even shorter shorthand for it, which is the backslash operator or matrix divide, which will immediately solve this system of linear equations. So this backslash operator does exactly the same as this P-in line here to solve this system of linear equations for the parameter X, list of parameters X. Okay, so that's how we solve these systems of linear equations. The remarkable thing is what I've written on the last slide here, that despite the fact that we haven't mentioned any kind of objective function here at all, it turns out that the solution that we get by solving this system of linear equations is in fact the least squares solution. It's the solution that minimizes the sum of square objective function that we were talking about in the previous section. Let's just work that through just to see, just to sort of convince ourselves that it's true. So if let's start from the least squares objective function itself. So here it is. And let's start by differentiating it, because we know that at the minimum point, at the minimum of the least squares objective function, that's the solution that we're looking for, and its derivative must be 0. So let's differentiate this objective function with respect to just one of our x parameters. I'll just pick one arbitrarily and call it xj. So d of f by dxj is then, we can differentiate this sum term by term, k is 1 to k. So it's going to be, so ak, of course, doesn't depend on xj because that's just the measurement, but the sk's do depend on xj. That's our model that has parameters x. So differentiating a term then of this objective function will look like minus 2 AK minus SK dSK by dxj. But of course, we're assuming a particular form for our model, S here, and it's this linear form on the slide. So we're assuming our model looks like this. So we can write S of K is some, using my big G's notation from, I'll use this big G notation from up here instead. So that then is G K I is 1 to n, xi, and so, and if we want to compute this derivative dsk by dxj, so that I think is just going to be gkj, of course, because the only term that depends on xj is the xj term in that sum. So there's only just its coefficient survives the differentiation. So then let's plug these back into our expression for the derivative of the objective function. So then we get df by dxj equals sum over k minus 2 ak minus, right, so let's put in this sum now for sk. I is 1 to n gki xi, all multiplied by this derivative gkj. And as we noted a minute ago, this of course equals 0 at the least squares solution by definition, because at the least squares solution, f is at a minimum point. So setting that equal to 0, then I think we can, let's expand this and then rearrange. So we can now write, well, I'll get rid of this minus 2. We can divide through by that since it equals 0. I can have k is 1 to k ak gkj minus sum over k gki gkj xi, all equals 0, or equivalently, these two things are equal to each other. Let's compare that to the equation that we had, the matrix equation that we had up here. This one here. Let me write that again down at the bottom. So that was G transpose A equals G transpose G of X. And I hope you can convince yourselves, if you look carefully at this, that this equation here is just one row, the j'th row of this matrix equation that I've written here. And since we chose J arbitrarily, that must be true of every row of this matrix equation here. The same calculation would work for any J. And so what that tells us is that the solution that minimizes the least square fit is the same as the solution to this matrix equation. So remarkably, solving this matrix equation gives us the least square solution that minimizes the sum of square differences. Okay. Not that we need that derivation particularly, but it's just good to understand that those two things are equivalent to each other. Right. Let's, before I move on, so actually, all right, I'll just do this slide since I've flicked to it. We noted earlier, of course, that it's easy enough to generalize the least squares fit slightly to avoid, to allow the noise variance to be different on all of the different measurements, and to get this weighted least squares objective function. Actually, the generalization of the solution is also quite simple. So to find the weighted least squares solution, we simply have to introduce this diagonal matrix W. So it's W is a diagonal matrix with 1 over the variance of each of the noise on each measurement on the diagonal terms, and we introduce that into the pseudo inverse in this relatively straightforward way to get the weighted least squares solution instead of the basic least squares solution. Let me just go back to this slide second, and just to make this concrete, let's go through again our sort of favorite simple example of the child's height measurements, and just construct this design matrix for some simple models for these data to see how this works. So once again, let me draw my 4 height measurements here. Our model, of course, will stick with the simple line model that we were using before. And let's think about the contents of these various matrices that exist in the matrix equation that we're trying to solve. So this is the h-axis, this is the age axis. So our vector A now contains, so this is the list of measurements, of course. The measurements here are the heights, h1, h2, h3, and h4. So let's put those into our matrix here, into our measurement vector, h1, h2, h3, h4. Of course, each of these we can write using our model. So h4 would be ma4 plus c. Let's think about our vector of unknowns. What are the unknowns here? What are our unknown model parameters that we're trying to estimate? Anyone tell me? Yeah, M and C. If we look at this equation here, we know the A's. These are the ages at which we made the measurements. These are effectively our device settings. We chose those and we know what they are. The H's here are our measurements. The model, of course, is parameterized by the gradient, the slope of the line and the intercept of the line, M and C. So let's write those in there. There we go. So all we need to do then is to construct this, this G matrix. And so, you know, going back to our sort of general picture of the G matrix up here, all it is the coefficients of the different unknown model parameters in the system of linear equations that we write out. And so you can see directly from here that the coefficient of M is the age, whereas the coefficient of C is just simply the number 1. So I can write then so the first row of our G matrix corresponding to measurement number 1 would just be the first age and the number 1. And similarly, the whole of the first column is the ages corresponding to each of those measurements, and the second column is just a column of ones. Okay, so that would be the design matrix for that simple line model of the ages. Let's think about a slightly more complex model. Suppose we don't really think a line adequately describes that set of data points. Oops. Oh, live transcription. Okay, there we go. So let's use a slightly more complex model. Here is one. Let's say P of A squared plus MA plus C. So we'll use that quadratic function of age instead. According to my definition on this slide, is this a linear model? That's a question for you again. Is it a linear model? Anybody? What do you think? Well, I'll put forward that I think this is a linear model, despite the fact that it has this clearly quadratic term in here. I think, according to my definition on the slide there, this is linear. But why does that quadratic term not matter? Any ideas? What's our list of what's the list of unknown parameters in this model? Now vector x. How is it different from the previous simple line model that we wrote down just above? Still linear in the parameters, correct? P, M, and C. The unknown parameters are now P, M, and C. A, of course, although we've got a quadratic term in A is not an unknown parameter. This is one of the device settings. It's one of the y's in this sort of general picture, and we can take any function of y that we like, including a square. It only has to be linear in the unknown parameters, the x's. And here our x's are P, M, and C, and H is linear in that. So we can similarly construct our matrix equation here and design matrix. The A vector, of course, looks exactly the same as it did before, same list of measurements. But now G will have 3 columns, one for each of the unknown parameters, and the last 2 are exactly the same as before. A1, A2, A3, don't need these dots, do I? A4. But of course, we've got a new first column that corresponds to the new parameter P, which just contains these A squareds. Okay. Here's another one. This one linear. Votes for yes. Zero votes for yes. Good. Votes for no. Zero votes for no as well. That's not so good, because clearly this is not a linear model, because we have the exponential of an unknown parameter m here. However, it's not very difficult to turn this into a linear model. If we take logs of both sides, let's take logs of both sides of this equation, we get log h equals log a plus m a. And now this is looking in a much more friendly form. We can, rather than using the original measurements h1 up to h4, if we think of the log measurements as our measurements instead, and write our vector a as log h1, log h2, log h3, log h4, and our list of unknown parameters is now log a and what's the other one, m, then actually we end up with a design matrix that looks pretty much the same as the one for our original line model. We've got the columns permuted, but we first have a column of 1s and then have a column of A's. It looks exactly the same. And we can solve that using the exact same machinery, just that we end up estimating log of A and M rather than the parameters directly. All right, one more. What about this one? Is it linear? No, thank you. Of course it isn't, because it's got an exponential in it again. But is there a way of linearizing this in a similar way so that we could use this kind of nice, simple way of finding the best parameters? Is there some similar trick that we might perform to linearize it? Well, the answer really is no this time. So because we've got this additional added term here, there's no way to turn this into something that is, there's no simple transformation that can turn this into a linear function of the three unknowns now, A, big A, little m, and C. So we're stuck, if we want to use a model like this, with having to use nonlinear optimization. Well, so so it's not a bad suggestion. Someone's saying what we might do is put on the left-hand side H minus C, and then use as our measurements log of H minus C. But the problem is we don't know C. We do know the H's, of course, but we don't know C, because that's one of the things we're trying to estimate. So that won't work, unfortunately.